We going? Fantastic. Okay, so this is a continuation of last week's little talk. Basically, I'm talking about the log structure in RAMCloud. That is, how do we store data in our storage system, both in memory and on disk. Just a quick review. For our purposes, there are basically two entities in the system that we care about. There are master servers and backup servers. Masters basically consist of a hash table that is used to look up entries within a log. Basically, we chop our DRAM up into 8 megabyte chunks we call segments. We kind of thread these segments together and append data to them when we store new objects and stuff. So for instance, at any point in time, there's some number of segments we've written to before and a head segment, which is the segment that we're currently filling, that we'll write new objects to. So if we write a new object, we store a new object in the system, we might write it at the end of the head segment here. The head segments are always buffered on multiple backups, just one here for simplicity. So if we're writing an object to the head segment, we'll first issue RPCs to all the backups before we reply to clients to ensure that that data is durable. And we assume that this buffer is in some sort of non-volatile memory, or we have battery backups or some other technology to ensure that if power goes out, we can flush these to disk. And basically, once we fill up a head segment, we will allocate another one on the backups, in the masters on the backups, and the completed segments will be flushed to disk in the background. I think where we left off last was we were talking about cleaning. So basically, with this log structure, you have this problem where you're writing objects to the log. You're never overwriting stuff in place. You're always appending stuff to the end. So that means that, for instance, if this write happened to overwrite this object, then basically you end up with some free space here. And over time, you end up with fragmented free space throughout the log. And you'd like to get all that back into a nice contiguous chunk so that you can write new data. So in order to do that, we basically have a technique somewhat similar to garbage collection called cleaning, which we basically borrow from log structure file systems. And cleaning is basically a simple 3-step process. You choose some segments to clean based on some policy. I went over that a little bit last time. So for instance, maybe we select these 2 segments to clean. They have some objects in here, some dead space, some live space. Maybe the red indicates what's alive and white is what's dead. You take those 2 segments, you scan them, you write out all of their live data into some number of survivor segments. So maybe copy all the live data down. You update references in the hash table so that they point to this new survivor segment. And then eventually you'll basically replace, hopefully, some larger number of segments with a smaller number of segments in the system, and whatever's left over is the amount of space that you ended up getting back. So I think we pretty much covered these 2 points. There are a few bits under this last point that I'd like to go over. So how do we actually free these segments once we've cleaned them? There are a couple of issues. One issue is concurrency. That is, it's possible in RAMCloud for there to be multiple service threads that can be servicing read requests. And the cleaner actually runs in parallel with the rest of the system. So it's entirely possible that you may have moved an object from this segment to this segment, but another thread actually has a pointer to the previous location of the object and is servicing a read request and issuing that pointer to the NIC, which is DMAing it and sending it out across the wire. So you can't actually recycle this segment until you know that no other piece of the system is ever going to access that data again. Does that make sense? So how do we do this? We have this mechanism we're calling epochs. Basically what happens is every RPC that comes into the system, so if you have a request coming in, we can use another color for a request. If you have an RPC that comes into the system, there's a global epoch number, just a 64-bit integer, starts at 0. And every RPC in the system gets tagged with this epoch number. So if we have an RPC coming in with a read. It gets tagged with epoch 0. And then what happens is when we've completed cleaning and we have some segments that we've cleaned and want to reuse eventually, what we do is we read the current epoch, store that with, we basically have some metadata on the side that tracks what segments we're waiting to clean. We store the current epoch with that, and we increment the epoch number. So at the end of cleaning, the epoch number will go to 1, so that all new RPCs are tagged with 1 rather than 0. And then what we do is, occasionally we scan the list of segments that we're waiting to free, and we check to see whether there are any, so I guess these guys reach tagged with epoch 1. Then we check to see whether there are any RPCs in the system that have an epoch greater than or equal to the epoch here. And if we don't, then that means that...
Less than or equal to.
Sorry?
Less than or equal to?
Correct, yeah, sorry. Less than or equal to the value here, and if we don't have any RPCs in the system, then they must have started after we had relocated all of these pointers into these old segments, which means that there's nothing in the system that could be pointing to these segments anymore, so it's safe to reuse that memory. So I guess how do we know which RPCs in the system have which epochs? Basically, there's a linked list of all RPCs. So you can just traverse that thing and take the max. Okay, so that tells us how we can free segments in memory safely. There's also an issue of when can we actually free these segments on disk. Yep.
So there's one epoch responding to a master?
Yeah.
And do they need to survive master crashes?
Oh, sorry. Question was, is there one epoch per master? Yes, there's just one integer. Does it need to be preserved across crashes? No. It's entirely soft state.
So this is useful only to determine what the outstanding RPCs are. That's it.
Yeah, it's only useful for basically reasoning about what's happening in the DRAM of a particular master. So these segments aren't actually tagged on disk with an epoch number. Okay. You'll never see an epoch number during recovery, anything like that.
So, but there is a tag with epoch numbers in the memory log?
Effectively, yes. There's effectively, I mean, there's not like a bit on a segment that says what it's not like internally. There's basically metadata on each segment that has an epoch number. If it was clean, this was the epoch when it was cleaned.
I see. And the metadata is not stored with the log?
Yeah, the metadata isn't stored in the log. It's completely soft state. There's no reason to persist it across recoveries.
If the master crashes, then all of those service threads are going to work.
Right.
This general technique, by the way, is used in a lot of places in concurrent systems to avoid locking. That's why it was done here, to avoid having to have locks, additional locks for readers to acquire. And it's for some reason, it's required the acronym RCU, if you hear that, read, which stands for Read, Copy, Update, which you can kind of roughly map onto the face of what's going on here. But the basic idea is that when you make a change, you make it so the old state continues to work as well as the new state for a while, so people could use either one. And then you wait until everyone is finished. Anyone who could possibly have used the old state is finished. And you know that any future people will always use the new state. And then you can finally, at that point, go and delete all the old state.
Yeah. So do we not have audio like at the camera anymore? Okay. So there's probably an awkward bit where I'm just staring off into space. John is commenting that this is very similar to something called Read, Copy, Update, or RCU, which is... I can't actually figure out exactly what RCU is supposed to stand for because it sounds like it basically has wrapped its arms around a whole bunch of different concepts, but one of them that they talk about is something called wait for readers primitive, where basically you have some way of saying, tell me when nobody else can read this memory address anymore, and then I know it's safe that I can free it. And one way of tracking it, one way of doing that wait for readers primitive is using some mechanism like this. I think operating systems do other stuff, like they can tell whether or not there are any other threads doing syscalls at some point in time, stuff like that. Okay. Yep, John?
You talked about readers, but what about writers?
What about writers?
Concurrent writers.
There are no, okay. Yeah, question is, talked about concurrent readers, what about concurrent writers? There are no, objects are never updated in place. So these pointers, what is pointed to by the hash table is basically immutable. So you could run into a situation where, it's not important, but you could run into situations where a service thread might be reading an object that happens to be an older version because you've since overwritten it, and there could be multiple threads actually accessing multiple different versions of objects at the same time. But that's...
I'm worried about a situation where the object is being moved by the cleaner at the same time that someone...
Oh, you're wondering about the hash table
and
consistency.
Said, well, or also, what about the tombstone? Do you end up with the cleaner moving the object to a new location, but the writer writes a tombstone that refers to the old location of the object?
Okay, first question, let's see. So there's something I left out here.
And the hash table too. Yeah, when you finish with the tombstone, you can talk about the hash table. You can end up with the right entry in the hash table.
So let's draw out a situation. You're saying I have a version of some object. I overwrite it in some other segment. I write a tombstone, and I write a new version. And the cleaner moves this guy to another, concurrently moves this guy to another segment. Write this to a survivor. And you're worried that this tombstone may refer to this segment. Maybe this is segment 5. Right? How do we avoid that situation? Let me think. So you cannot actually... Okay. Yeah, so basically, just have to kind of page this all in. Basically, we use the same mechanism we use to protect the hash table buckets. So basically, at the start of the overwrite RPC handler, it will hash the key for the object that you're overwriting, and it will grab a giant lock around the bucket that points to that object. And the cleaner will actually do the same thing when it tries to relocate that object. So what will happen is, if this RPC comes in first, it'll grab that lock. The cleaner will not be able to move this object to the new segment. It won't even be able to check if it's alive or not. The cleaner will move it. The cleaner will... You'll write the new tombstone, the new object. You'll update the pointer in the hash table. You'll release that lock. The cleaner will grab the lock and notice that it's in a different segment. So I think that's safe. It's probably a little...
It has to lock the hash table for every object it cleans that has to lock a hash table lock.
Correct. Yeah, and you have to obviously be careful about when you take the lock, because you don't want to check first and then lock and have a race condition. So yeah, it's actually... so behind the scenes, there's actually a table of bucket locks. So basically, we use fine-grained locking on the hash table because we might be accessing it concurrently. And basically, there's some separate array, smaller array of bucket locks. I think there's like a 1024 spin lock, something like that. And various larger chunks of the hash table map onto different locks in this bucket. Turns out that seems not to be a big bottleneck at this point, so that's why we went with that. You probably do much more complicated stuff, but then you'd have to worry about nasty issues like this sort of thing. So for simplicity and correctness, I think that's kind of a reasonable way to go. Okay, so that's how you can free segments in memory. There's also an issue of when can you free segments on disk. Because, for instance, it would really suck if this segment were not written to disk or weren't made part of the log before you delete these guys, because then you'd effectively lose all the data that was contained in these segments when you end up replaying the log. So that's actually a much, let's see, concurrency in memory. And then I'll call this consistency on disk. And this is handled much more simply. Basically, we have, I talked about log digests last time, so at the beginning of each head segment, we basically have a list of all the identifiers for all the other segments that make up the log, so that if you have a crash, you can find the head segment, read out the log digest, and you know all the other segments that you need in order to replay the entire log. And so basically, if you want to free these segments on disk, you have to ensure that they are removed. Well, you have to ensure that the survivor segment has been added into the log first, and this is actually a simple opportunity to basically atomically swap the two. So what ends up happening is if we fill up this log head and write a new log head, then we end up writing a new digest that includes this segment and excludes the segments that we cleaned. And then after that point, you're free to issue RPCs to the backup saying that you can free these guys on disk. So basically, you just have to wait until the head segment rolls over to the next one after your cleaning pass completes.
Is it okay to write a new digest before those survivor segments have been flushed, all the backups?
Is it okay to write a new log digest before the survivor segments have been flushed? You mean flushed to disk or before they're fully updated?
Flush to backups.
They have, I mean, you have to ensure that these segments have been completely replicated to the backups. They don't have to be flushed to disk necessarily, and we assume that that's all kind of safe. Any questions? Okay. Yeah, there's a little bit of a funny corner case. It's not like super conceptually important, but you might wonder what happens if we don't have any head segments that we can write to. If we're completely out of memory and we clean, then we need a segment in order to get segments back. That seems like that's a little bit of an issue. So what we basically do is we reserve a couple of emergency head segments, is what I call them. This basically addresses the problem that you need some segment space to actually free some space. And so an emergency head segment is just like any other segment, except you cannot write any data to it. And that's an important property because that means that you don't actually have to clean this thing. You can basically throw it out immediately. It doesn't contain anything interesting aside from a log digest. And we basically keep two of these emergency head segments in reserve so that if we're completely out of memory, we can swap between the two. We can, if we're out of space here and we want to free these segments, we can allocate one of the emergency head segments. If for some reason this didn't actually net us any free space, that would suck, but we could always use after the next cleaning pass, we could use the other emergency head segment, drop the previous one out of the log. You can swap between these two. Okay. All right, so on to somewhat newer stuff. So there's a bit of a problem with this scheme. And the problem is that we've tied the formats of the memory and disk logs together. Oops. Weird. And what I mean is, I talked a little bit last week about how the amount of work it takes to do this cleaning step is related to the utilization of the segments that you choose to clean. So basically, the cost to clean a segment with utilization U, meaning that where is between 0 and 1, meaning that U is basically the percentage of live data, is I think it's basically 1 over 1 minus U. So the problem is basically the more space you're actually actively using in your system, the less free space you have in each of these segments, the more expensive it is to clean each of these, because you have to write more live data to get fewer bytes of free space back each time. So if you run your servers at 90% memory utilization, you end up having to pay basically 10 times as you have to do 10 times as much work to store each byte of data, because you basically have to copy 9 bytes out of each of these segments to free out a byte that you can write some new data to. And by tying the memory format and the disk format together, that means that every time we clean, not only do we have to shuffle stuff around in memory, which is actually, it's not terribly onerous because we have a lot of memory bandwidth, but we also have to write all this data to backup disks, which means we have to go over the network, and then eventually we have to flush these out to the disks themselves, which have much more limited bandwidth. So eventually we become bottlenecked, not on kind of the capacity of cleaning within the DRAM of the server, but on kind of the I/O that we have available on the backups. Does that make sense? Okay. So one kind of obvious solution is to decouple these formats.
Well, a simple solution is just to don't use the backups at very high utilization. It's cheap, right?
Sure. Simple solution is don't use very much of your memory, and then everything's cheap. Then cleaning's cheap, but your system's very expensive. So if you're incredibly wealthy, maybe that's a reasonable solution. But presumably you'd like to use some reasonable percentage of the resources that you have. So, right. So, is it possible to break this tying together of the in-memory and on-disk logs? Let's see. So I guess you could present a straw man and say, well, why don't we do cleaning completely independently? We'll have some segments in memory, we'll manage them with a cleaner, we'll have some segments on disk, we'll manage those guys with a cleaner. The segments in memory won't actually correspond necessarily to what's on disk. They're basically two completely separate entities. Now the problem with that is then either we need to, so if we completely decouple, then that basically means that we either have to read off of disk when cleaning, because we won't really know what objects are in each segment on disk because we're not actually keeping track of that in memory. You can either do, let's see. So if we completely decouple, you have to either read all the segments off disk when you clean, or what was the other problem? Or if you really want to keep this property, then you basically have to still keep track of every segment's contents on disk. So if you know what objects are on which segments on disk, then you wouldn't actually have to read these, so you wouldn't have to pay the I/O cost of going to backups. But then you're actually paying some additional memory cost because you basically have to keep a list for every segment of what objects are contained in that segment. So we have a slightly different solution. This is a major bullet. So our approach is somewhat simpler and avoids these issues, and it's something we call memory compaction. So what we do is we basically have two separate cleaners in the system. We have the old cleaner, which we call the combined cleaner now because it frees space in memory and on disk. And then we have a memory compactor. What the memory compactor does is it will run and basically squeeze out the free space in a single segment. So for instance, if we chose to compact this guy rather than clean it, what it would do is it would move all the live data to the front of the segment, and then it would free the space used at the back of the segment. Yep.
Wouldn't that give you Swiss cheese size segments?
Yeah, question, doesn't that give you Swiss cheese size segments? Yeah, basically. And there's a bigger issue of...
Cheese in the home system have holes in it.
Well, I mean, line up
It's
two
variable
segments.
size.
If you line up two segments and you freed off this second half of your first segment, aren't you going to have holes in your memory?
Yeah, you need some way of getting that space back. Yeah, so this is where things kind of turn slightly unfortunate, I think.
Why don't you finish exploring the basic two-level cleaning mechanism though, before you start going into the solutions that have this problem?
Finish the two-level cleaning solution. I think that's mostly it. I mean, otherwise, I could talk a little bit about.
Talk about how to get you the best of both worlds.
Ah, okay. Okay, yeah, great. So, what's kind of the point of this? What benefit do we get? Well, so basically, what the memory compactor does is it's kind of a less efficient version of cleaning. You can't. Cleaning gives you the ability to reorganize the data in intelligent ways, and hopefully in the future that pays off and you can clean a little bit more cheaply. A memory compaction always operates on the same segment. Objects can't kind of change which segments they belong to because then that would cause kind of the segment on disk to differ in contents from the segment in memory. So what memory compaction basically lets us do is take advantage of the fact that we have a lot of memory bandwidth in the server. If we don't have to write anything to backups, then we can actually copy a lot of data around. We can update a lot of hash table entries very, very quickly. So we can expend quite a bit of resources compacting segments in memory. And what that ends up happening, the result of that is basically, if we can take the memory that we free at the end of the segment and basically stitch them together and form new segments, then we're able to continue to service writes. And what ends up happening is we have some larger number of segments in memory that are slightly smaller than, or maybe half the size on average than the original 8 megabyte segments. And then on disk, we have this much larger log that has a bunch of full segments in it that contain objects that had been previously compacted out of memory but are only present on disk. And basically the result of that is that the effective utilization of these segments on disk drops. And so the longer that we put off cleaning, doing our combined cleaning to basically reclaim disk space, the cheaper it becomes. Because eventually, we might end up with all 4 megabyte segments in memory, and we'll have the same number of segments on disk, but they will have half of their data will be dead. So cleaning, when we clean them, we'll only have to clean it basically effectively like a 50% memory utilization rather than, 90% or whatever the system is running at. Does that make sense at all? It's a lot of babbling and not a lot of pictures, so I don't know. Okay. So that's kind of the general gist of memory compaction. So by having these two cleaners, basically we can exploit all the bandwidth that we have on the master servers and do a lot of work to squeeze out a lot of free space. We can exploit the fact that our backup disks hopefully have a lot of extra space that we otherwise wouldn't be using because disk is much cheaper than DRAM. So basically we can kind of combine the large space here to get cheaper cleaning in the future and the high memory bandwidth here to get basically squeeze out space without having to write stuff to backups. Okay, so that leaves kind of an important problem. That's how do we recoup the space at the end of segments?
in memory. So.
Yes. And so it's actually not probably terribly foreign to anyone who's seen virtual memory before. Basically, we divide segments up into seglets. So what happens is, now in memory we have, if this is a segment in memory, it's normally 8 megabytes. What we do is we chop it up into a bunch of fixed size pieces that we call seglets. Each of these happen to be currently 64 kilobytes in RAMCloud. Why 64 kilobytes? Because that means that on average we'll probably waste, due to we'll probably have half of a seglet's worth of free space fragmented at the end of each segment after we compact it, because we're probably never going to, or it's unlikely that we'll always hit an exact even boundary with the amount of live data in there. Having 64 of these means that we have 128 seglets per segment, so you only have at most 1%, less than 1% fragmentation. So yeah, so basically we have kind of in software broken up segments into kind of large pages that we stitch together also in software to represent large 8 megabyte segments. And basically what that means is that your objects are no longer contiguous. So if, for instance, you're writing an object into the segment here, and it happens to span multiple seglets, this is actually kind of not representing virtual memory anymore. This seglet points to somewhere in memory. This seglet points to somewhere else in memory. And what you end up having is a little bit of an object over here and the front of the object over here. Make sense? Okay. So this seems a little bit weird. How does this affect the system? How do we actually work with objects that are kind of split up like this? It actually turns out to be not that big of a problem, at least right now with our simple data model. Basically, what happens is, maybe I'll walk through step by step. Imagine that you have a read that comes in. First of all, I guess an obvious question is, well, what does the hash table point to now? You've got this object. You can't just point to the front of the object and dereference a struct, for instance, because who knows where it's split up over memory. So basically what happens is the hash table will point to the beginning of an object. So it's a direct pointer to the beginning of an object. It's very easy to determine whether this object is fully contained in one seglet or not. And if it's fully contained in a seglet, then you basically have no problems. You can just play around with that pointer. Everything's fine. The reason why it's very simple is because seglets are fixed sized. They are always aligned on 64, and they're always aligned on 64 kilobyte boundaries. So you can do a little bit of math to figure out where am I within, this pointer points to somewhere within a seglet. What's kind of the offset of the pointer within that seglet? You can read out the length of the object, which is stored at the very front of the object, and then figure out how far am I from the end of the seglet? Do I span multiple seglets? If I don't span multiple seglets, no problem. It's just like before, pointer basically points directly to an object. If you do span multiple seglets, on the other hand, then you have a pointer to the front of it, but then you have to figure out, well, where does the rest of the object live? And so what ends up happening is, the system maintains a big table, a seglet to segment table. And basically for every seglet in the system, so these are seglet indices. So all of our seglets are actually allocated from one giant contiguous chunk of memory. So given a pointer into any seglet, you can figure out very easily, well, given the pointer and the base address for all the seglets, you can figure out which seglet number is it in the system. You can take that index, jump into this table. So let's say this is seglet 3. You could jump into index 3 in this table, and it will give you, there's a segment class pointer. And within the segment class is just a list of all the seglets. And so you can just traverse that list and figure out, okay, I know that I am the first seglet in the segment. I know that my object spans 2 seglets. So the next seglet is also contains part of this object, and you can pull out the pointer for that.
Is that going to be a cache miss then every time you cross a seglet boundary, because you're going to miss in the seglet indices table?
Question is that going to be another cache miss every time you do a lookup? Every time you do a lookup for an object that spans multiple seglets, yeah, it will probably be another cache miss. If you have small objects, if you have 100-byte objects, it's quite rare that an object actually spans multiple seglets, so the vast majority of the time you'll never have to jump through this table. If you have large objects, then they're kind of expensive to process anyway, so an extra cache miss probably shouldn't make much of a difference. So that's the reasoning behind that. The current RAMCloud code actually does something kind of stupider. It kind of somewhat analogous to this, but takes a slow path for every single lookup. This is how the system will be once I push my changes, which I have every intention of doing. So if you look at the current code, it might look slightly different than this. Hopefully not for long. Okay, let's see.
Good question.
Yeah.
Is it easy for us to change segment sizes within RAMCloud? So if we
Yeah, it's a pound define. Actually, no, it's a runtime. You can pass a parameter to the server. Yeah.
One can imagine that you might have large objects at some point, like you're going to have a lot of large objects, so you can increase the segment size? Or would that still cause you to waste a lot of space? I'm just thinking about whether you can avoid those cache misses if you just resize your seglets for larger objects.
If you have larger objects, it probably doesn't matter. So I guess the question was, would it make sense to use larger seglets if you have larger objects stored in the system? I don't think it probably makes much of a difference, because if you have large objects, then if your objects are, I don't know, 64 kilobytes or something pretty big, it's going to take a reasonable amount of time compared to a 100-byte object, to send that thing across the wire. So I imagine, the extra bump in latency, like the extra, I don't know, 50 nanoseconds or whatever it takes to jump through this table, or maybe you have to jump through it a couple of times, but I imagine that time would be relatively small compared to the extra time that you'd have to pay just because you're processing a large object. So, interesting question. I mean,
Are there any conditions under which you could imagine a smaller or larger seglet size might make sense?
Question was, are there situations in which you might imagine that a smaller or larger seglet size might make sense? With an 8-megabyte segment, I don't really see a benefit to going smaller than 64K. I mean, the reason 64K was chosen was because basically if you have a little bit of fragmentation at the end of a seglet, then it's going to be relatively small compared to the entire size of the segment. So, if it turned out that memory compaction was actually generating very, very small segments, that you were compacting such that you always had maybe a 1 megabyte segment, then maybe 64K relative to 1 megabyte is a little bit too much for you as compared to 64K relative to 8 megabytes or 4 megabytes or something like that. So maybe you'd want to drop it there. But I think, I don't know if you guys have other ideas, but I think the main benefit of going to a smaller seglet is just reducing the fragmentation across seglets. And then the benefit of going to a larger seglet is that you reduce the probability that you actually have to traverse multiple seglets. But then if you go too large, then you probably want to bump your segment size, because then otherwise your seglet is relatively large compared to that, and you might waste more memory. So I think those are kind of the fundamental trade-offs. Okay. So just in terms of implementation, you might be wondering, well, this sounds like kind of a pain. What happens if I'm coding in RAMCloud and I have to support the fact that an object spans multiple seglets? That sounds kind of gross. There's a class called buffer, which was originally written for the RPC subsystem that basically does exactly what we want. It tracks multiple discontiguous chunks of memory and basically gives you a nice interface so you can iterate them in order, or you can squeeze them down into one contiguous chunk. So what ends up happening is when you read an object, you basically get a pointer into the log, and you have a way of converting that pointer into a buffer. And most of the time, that buffer contains just one pointer inside of it. Sometimes it contains multiple pointers, but everything's kind of hidden under the interface. Right now, if you actually access an object that spans multiple seglets, it will copy it to some other area of memory. I think it actually does a malloc if it can't write it into some relatively small stack buffer. So, so far that hasn't been too terribly onerous in terms of coding, but I don't know if Arjun has other opinions on that since he's been... Okay. Let's see, okay. So there are a couple of kind of weird issues having to do with tombstones that this memory compaction scheme brings up. So, I guess I went over tombstones previously. Tombstones are just pieces of metadata that we use to indicate that objects are deleted. They're only ever used during recovery. So basically, we really only care about them existing on the disk logs, because if we replay those logs, we want to make sure that any object that happens to be in the log that was deleted has a corresponding tombstone so that it doesn't come back to life. The issue with tombstones, however, is that the main issue is that memory compaction alone can't get rid of tombstones. So last time I mentioned how you determine whether or not an object is alive or a tombstone is alive. An object is really simple. If you're cleaning a segment and come across an object, if the hash table points directly to that object, then you know it's the most recent one, it's alive. If it doesn't, then it's something old and you don't need to keep it. For tombstones, there's no reference in the hash table. It doesn't really make sense. What we do is we keep tombstones contain a 64-bit segment identifier. And basically what the cleaner does is, or well, when you overwrite or delete an object, you place a tombstone into the log, you include the segment that ID that contains the object that was deleted. So for instance, if this is a tombstone for this object, it will contain segment ID for this segment. And when the cleaner is processing segments, if it sees a tombstone, it just checks to see whether that segment still exists. If it does, then that means the object still exists on the on-disk log, so you need to keep that tombstone around. If the segment doesn't exist, then that object can never be replayed, so you can throw that tombstone out. But since memory compaction does not actually change the contents of the disk log, that means that if you're just running memory compaction over and over and never run the combine cleaner, that tombstones basically will pile up. Because every time it comes across a tombstone, it says, does a segment exist? Well, yeah, it's still on disk. We haven't gotten rid of it. We haven't actually modified anything on disk. So what ends up happening is eventually your free space starts to fill more and more and more with tombstones. And that means that your effective memory utilization goes up and up and up because these tombstones are effectively alive. So there's less free space in each segment. And you have to do more work to get fewer bytes back. So basically, eventually your system will kind of grind to a halt because it's getting more and more and more expensive to clean, and it can clean at a slower and slower rate. So this basically means that eventually we need to run the combine cleaner to basically shake some segments out of the system so that the tombstones that refer to those segments now don't actually refer to anything that's still in the log. And then either the memory compactor or the combined cleaner can get rid of those corresponding tombstones. And there are a bunch of kind of policy issues of how do you choose which cleaner to run, because you certainly wouldn't want to just keep running memory compaction until the system stops making any progress. You probably want to run it somewhat earlier. And it turns out that kind of what the optimal balance of these two cleaners actually depends a lot on the workload. And I won't really get into that. It's not super well understood at this point. Okay. There's also another minor problem with tombstones. And that is, how can we track which tombstones are alive? So basically, tombstones die when you clean a segment on disk and you get rid of it. But there could be tombstones spread out all across memory and any other segment that happen to point to objects that used to be in that segment, deleted objects. And so what you'd really like to know in order to make intelligent cleaning decisions is, for each segment, exactly how much of the information contained in it is alive and how much of it is dead. But with tombstones, for one, with combined cleaning, it's hard to keep track of that information because basically, if you throw away a segment, it can affect little bits stored all over the system throughout memory. And actually, it becomes impossible with memory compaction because what ends up happening is the memory compactor can throw out an object in memory. And then once you actually run the combined cleaner, so imagine there was some object in here that had been thrown out, it has a corresponding tombstone somewhere. When you do run the combined cleaner, you're actually running the combined cleaner on the in-memory segment, and so you'll never see that object. So you would never actually have an opportunity to say, aha, I'm throwing away this object. I should go find its tombstone and keep track that I actually deleted it and update some statistics for that segment. So because of this, RAMCloud does basically periodic scanning of segments in memory for tombstones. And basically what it does is it keeps track of two pieces of information for each segment. One is when it was scanned last, and the other is how much space corresponds to tombstones that we don't already know to be dead. And I like to refer to them as undead. And that's basically it. There's some policy about how often do you actually want to run this thing. Basically, what's implemented now was kind of chosen randomly and empirically. There's nothing terribly interesting there to talk about, I think. Yep.
Can you elaborate a little bit on why memory compaction makes the tombstone problem worse? Because I thought that memory compaction never just deletes segments. So why would it make it worse that you can't get rid of tombstones that point to a live segment?
The question is, why does memory compaction make the tombstone problem worse?
Yeah.
Well, so basically, do you understand that you can't remove a tombstone
Until it's removed from memory, sure.
until the object that it refers to is removed from the disk log.
Mm-hmm.
So then if you're only running memory compaction, you're never actually removing segments on disk.
Oh yeah, so I mean that makes it so you can't actually delete those tombstones.
Yeah.
But I mean, I thought you were saying that it makes it harder to find them.
It makes two things. Well, it makes cleaning more expensive, but I think what you're saying is it makes keeping statistics on on how many tombstones are alive basically impossible.
That harder?
I don't think you could have kept those statistics anyway.
You could have. You'd basically need to keep back pointers from each object that you delete. So if you wanted to keep statistics perfectly, if you're only doing memory or combined cleaning, basically, you know, if this is a tombstone for this object, you could overwrite this object, kind of violate our immutable log rule, to point to this tombstone so that when you delete this object, this guy goes away. But then you also need a back pointer over here, because it's possible that you might clean this segment first and move the tombstone, so you need to be able to update this pointer. Does that make sense?
I see. You're willing to break the immutability of the law, then you have problems with the whole epoch system.
Yeah. So yeah. Then you have issues with the epoch system because you're overwriting stuff. I mean, you could actually use the epoch system to do that.
It was pretty hard to begin with.
Memory compaction makes it, I believe, impossible. Previously, it was nasty and kind of difficult. Turns out that this is not very expensive. I think especially when you kind of optimize around this, basically multiply these two things together. The longer it's been since you scanned a segment, hopefully the more tombstones have gone away, and you certainly prefer segments that have more tombstones that you might actually be able to determine are dead. Does that make sense? Okay. I think that's it for two-level cleaning. So I think I wanted to talk about parallel cleaning, but I think that's, for the most part, that's been covered already. So the cleaner actually runs, I think I've mentioned this a few times before, completely in parallel with other operations that are happening on the server. In particular, you can be writing to the head of the log. I have multiple log heads. You can be writing to the head of the log as you're actually copying data to other survivor segments. In RAMCloud, we actually have kind of a generic mechanism called side logs, where basically you can just allocate segments, stuff a whole bunch of data into them, sync them to backups, and then inject them into the log. And the way you inject them is just by updating the log digest in the next head segment. Yeah, so I don't know, does anyone have questions, concerns about how this stuff runs in parallel? I think I've kind of
running in parallel, or many cleaners running in parallel?
one cleaner, many cleaners, many threads, servicing requests.
Some concept of many cleaners. You don't want two different cleaners to both decide to clean the same segment, right?
Right. Yeah, sure. So, yeah, you don't want multiple cleaners to choose the same segment. Basically, there's a module that tracks all the segments that you could clean. It determines what the best ones are to do combined cleaning on, as well as memory compaction, and it has a monitor lock around it. So hopefully the system will not choose the same segments to clean. Yeah, and basically, I think for the most part, just having these bucket locks around the hash table allows you to run many cleaners in parallel, many request threads in parallel. The epoch system helps ensure that you don't free out memory before someone's done using it. I think that basically covers parallel cleaning. I think I'm pretty much through with everything. I thought it might be useful to go over kind of at a high level what all the classes are that implement this stuff and kind of the basic functionality that each of them provide. So I think aside from the backups, if you just focus on everything here, it's, I don't know, 10 or 20,000 lines of C++. If you count unit tests, it's probably closer to 20,000. But it's all, I think, relatively straightforward and broken up into a bunch of kind of orthogonal classes to some extent. So there's a simple hash table class. This basically implements the master's hash table, points to objects in the log. In recovery, it might point to tombstones. I don't think I really want to get into that. think I mentioned last time, it's a very simple implementation. It uses closed addressing with chaining. So basically you hash into a specific bucket. If it's full, you allocate more memory. You have to walk a linked list. Statically sized, we never resize that thing. The log class, basically all the log class does is manages the head segment. And it provides a nice interface for accessing, basically, most of the time writing data to the log. As I mentioned, there's also this side log class, which basically allows you to append a whole bunch of data in bulk. We use that right now only, actually we might use it for migration, but mostly we use the side log for recovery because we want to take a whole bunch of data in from some failed master, cram it into the log as quickly as possible, and basically we only care about atomically writing everything. So we can, Ryan can go into this, but we can relax a lot of backup constraints and make it a little bit more efficient. So this is basically used for bulk writing of large amounts of log data and kind of atomically fusing it onto the log. Let's see. There's an abstract log class. This basically just provides common interfaces for log and side log. So they basically have the same API. I think side log has an extra method that's commit or something like that that basically ensures that everything is synced and stuffed into the log before it returns. Let's see.
That must mean there's some code that you call that sometimes appends to a side log and sometimes appends to a real log, and you don't want to know which one it's actually appending to? What would be an example of such code? Because if every piece of code always used either a log or a side log, and never the other, then you wouldn't need abstract log, right?
Question is, why do you have abstract log? Presumably that's so that you have this common interface so that there's code that can use either. Actually, it's more so that we can take common functionality from these two and stuff them in one superclass. So I don't think right now there's any code that would switch between these, and in fact, there are slightly different methods that you'd call. Like I think side log has a commit method rather than a sync method that the log has to ensure that everything's made durable. So you could probably change the commit and sync functions slightly and use them interchangeably, but I don't see a reason to. So it's just code sharing for now. Segment manager. This is kind of the core of the in-memory log. It basically keeps track of all segments. It's used to allocate new head segments. It uses the epoch mechanism to free segments that the cleaner is cleaned. The cleaner will actually interrogate segment manager to learn of segments that it can clean. Let's see. So that naturally leads to segment. So the segment class, basically all it does is it keeps track of a bunch of seglets and basically allows you to append to this discontiguous segments. If you're writing an object to the head of the log, basically what you're doing is calling into the segment class and saying, store this thing. I don't know how you really manage your seglets. I don't even know about seglets. Write it somewhere, give me a pointer back that I can later call you with to make sure that it's contiguous and so on. And it defines the format of segments. So last time I talked about how everything written into the log is called an entry, and every entry has a little bit of metadata that we use to determine, first of all, what the entry is, what type it is, and how long it is. And we can use that to iterate segments. This class is responsible for generating that metadata and for the format that we use. There's this kind of nasty subclass of segment called log segment. And basically what this does is it adds a ton of soft state to segment. So basically anything that really doesn't belong in segment, but that various other classes in the system use, such as statistics about what's live, epoch number, even the segment ID in the log, because the segment doesn't really know that it's part of a log. So stuff like that. So most of the system will actually deal with objects of type log segment rather than objects of type segment. There's a class called Seglet allocator. Basically, this thing just is what you use to allocate seglets. This is slightly non-trivial because it needs to ensure that it has separate pools of seglets for regular log writes. So if you allocate a head segment, then you'll allocate from one pool. You need to reserve some for cleaning. And you need to also reserve some for those emergency head segments that I mentioned before. And it maintains that seglets to segment table. That's used when you look up objects that aren't contiguous in the log.
Why wouldn't segment do that?
Then it is the other direction for segments.
Why wouldn't segment do that? Well, then what would you, the question was, why wouldn't segment implement the seglets to segment table? Well, then what would you do? You'd have a static, you have some static, or, right, yeah. You need, because you have one seglet allocator for the system, you have one segment instance for each segment. So I guess you could make some static nastiness, but then that would probably break all of our tests because we want to be able to instantiate multiple RAMClouds in the same address space. There's Object Manager. Basically, this is what handles all of the object operations. So it handles reads, writes, deletes. It replays logs during recovery. Basically, it takes RPCs in, or it takes arguments from RPCs, and it calls stuff on the log and stuff on the hash table to manage the objects in the main memory of the system. It also handles relocation of log entries. So when the log cleaner comes across some object, it doesn't know what the thing is. It doesn't know whether it's alive, whether it needs to be moved, and if it's moved, what metadata has to be updated for that. So it actually calls into Object Manager and says, hey, I got this thing. I'm going to give you the choice of moving it now, and I'll tell you where it goes, and you better update your metadata. Otherwise, tell me you don't need it, and I'll get rid of it. let's see. Master service used to actually implement everything in Object Manager, but we basically ripped all that functionality out, and pretty much all it does now is, at least for these object operations, it unpacks RPCs. So Object Manager doesn't know what kind of the wire format of any of the requests coming in is. So master service will pull out all the arguments and basically just pass them straight to Object Manager. Let's see. There's an important one. The log cleaner class basically implements both memory compaction and combined cleaning. So all the policies for determining which of these two to run, how many of them to run in parallel. It has all the logic that relocates objects by basically calling into Object Manager for each one. It interacts a lot with both Segment Manager to allocate survivor segments to write data to, as well as to learn about new segments that have been recently added to the log that it can clean. And it also interacts quite a bit with this other class called, make sure I didn't write it, called Cleanable Segment Manager. And this, actually I kind of lied. Cleanable Segment Manager is actually what implements the selection policies for cleaning. And it also does the tombstone scanning. I think that's basically it. There's also this key class that just basically wraps table ID and string key pairs, implements the hash function that we use to determine which bucket to jump into the hash table. I think that's more or less it. Questions? Yeah.
Does the hash table, you have a separate hash table for each master?
Correct.
And if so, how do you manage which object is actually on which master?
Question was, do we have a hash table per master? Yes, we do. Second question was, how do we determine which objects go to which master? So basically the coordinator maintains, so somewhere else in the system there's a centralized coordinator, and it maintains a bunch of metadata about the cluster. So it has some structure that tracks the tables in the system, and then each table, I don't know exactly know how this is formatted anymore, but each table actually consists of multiple tablets. So a table is basically just a 64-bit hash space, and a tablet is some contiguous range within a particular table space. So right now, generally, RAMCloud's pretty simple. You'll create a table. It will allocate the full 64-bit hash space to a single server. You have the option of breaking it up into any number of even-sized pieces if you like. Then it'll spray them across multiple servers. The client will, when trying to read or write an object, it will check to see whether it knows. Well, first it will hash the table ID and the key, and it will say, okay, do I have the data that tells me which server I think this well, so I have a hash value. It falls into some range. Do I have metadata that tells me which server is supposed to be responsible for that? If it doesn't, it goes to the coordinator and basically downloads that, the latest information, and caches it. And then it can talk directly to the server that's supposed to be responsible. Does that make sense?
You wouldn't want to have a central hash table anyhow, because that would mean that every read and write request would have to pass through one machine to go through that hash table. Because you'd like to be able to communicate directly from a client machine to the server that actually stores the relevant data.
The comment was you wouldn't want a single centralized hash table anyway, because you'd like to talk directly to the machine that owns the object rather than jumping, I guess, to some index server first. Yeah.
So once the client has cached this mapping from the coordinator, and if that mapping changes, say some tablet has been migrated to a different master, so what happens on a read from the client? So the client is going to issue a read to the master that had the data initially, but now it's not going to find it.
Mm-hmm.
So is it going to retry by contacting the coordinator to get an updated version of the mapping?
Yep. So the question was, what happens if, so I haven't drawn a client, but what happens if a client has a cache of what servers own some particular tablets, and that's out of date, and it contacts the wrong server? The server will say, sorry, I don't know what you're talking about. You better go back to the coordinator. And the client will contact the coordinator and get the latest list, and hopefully everything works out.
So if for it to determine that an object is not there, it needs to go to RPCs.
In order to determine that an object is not there.
Because the first time would fail, and you're still not guaranteed whether.
No. Oh, I see. Okay, so there are two responses. If you contact a server that's responsible for a certain range, and it knows that it owns that range of a tablet, and you say, I want to read this object, it will say, and if the object doesn't exist, it will say, it doesn't exist. I own this, and I'm telling you I don't have it. Like this is definitive. It doesn't exist. There's a different status. I don't know. I think it's called like unknown tablet or unknown table or something like that. So if it doesn't know what you're talking about, it just says like, look, I don't know what you're talking about. You better check with somebody else.
See, I'm not responsible for this object is one response. Another says, yeah, if it existed, I would know about it. I'm telling you it doesn't exist because this is my responsibility.
Yep.
So it will be, if you go to the wrong server, it will take 2 RPCs. Go to the wrong server, then go to the coordinator, actually 3. Go to the wrong server, then you have to go to the coordinator to update your cache, and then you go to the right server. But of course, after that, your cache is now up, so you won't make the same mistake twice.
Does the coordinator keep track of the clients that are running? Or?
The question was, does the coordinator keep track of running clients? Now it doesn't at all. I don't know why it would need to.
No, so
Nobody really does in RAMCloud.
Yeah.
Well, in one possibility, you can consider an active notification system where the coordinator can notify the client of any updates. So, I mean, I guess there would be a lot of bandwidth increase, but
Yeah, I don't know what benefit it would be for the coordinator to disseminate those sort of updates.
Because we can avoid multiple RPCs, right?
Yeah, but I mean, it's one RPC. You move a tablet somewhere else, the first RPC has to update the cache, and every other one is fast. So
Tablet motion is a pretty unusual operation.
yeah.
You're not going to be constantly moving. It's very expensive to move a tablet anyhow, so, because you're copying all the data. So.
Okay. I think we're done then.